In this video, we're going to take a look at the inclusion-exclusion principle to do with permutations. So remembering a permutation is looking at the arrangement of objects. This inclusion-exclusion principle is also known as the addition principle. And what we use it for is to determine the number of elements in the union of two or more sets. So when we think about that idea of the union of sets, it takes us back to our previous year's work on probability rules. And you might recognise this rule as more like an addition rule for probability, but instead of the P, we've just got N for saying how many. And it's saying that the union of two sets, which we know by this notation, the union is talking about either A or B or both, says that we can add all of the elements in set A and set B and subtract any elements that are in both, just so they're not counted twice. Let's have a look at a two-circle Venn diagram just to remind us of these situations. In a group of 24 people, 14 have blonde hair, set A, 10 have blue eyes, set B, and 5 have both blonde hair and blue eyes. We want to find out how many have blonde hair or blue eyes. So we've drawn a Venn diagram, a universal set of 24, and we can see that the number in A is 14 and the number in B is 10. But if we add these two circles together, we can see we've added the middle bit twice. So we want to take away the intersection of both sets, which will be 5. This will leave us with the number, we scribble that out, in A or B, in either. And that will leave us with 19. So 19 have blonde hair or blue eyes. This is a really nice rule to remember when we're dealing with different sets of elements or objects. We could also extend this rule to look at 3 circle Venn diagrams, so dealing with 3 subsets. What that requires us to do is to think about the regions in our Venn diagram when we're adding those totals together. So let's consider 50 people and their favourite physical activity. Of the 50 people, 25 said archery, 21 said baseball and 18 said cricket. 9 said archery and baseball. So I've placed that 9 just in this crevice here, which is going to represent this whole intersection between archery and baseball. We've got 7 who said baseball and cricket, and 8 said archery and cricket. Just make sure you can identify those numbers on the Venn diagram. All 50 people stated at least one of these activities, so how many stated all 3? So a slight change to finding the union here, we're going to try and find the intersection of all 3. So we're going to take that idea of adding up the totals together to find this unknown x, if you like. So saying that the number in A, which is 25, and the number in B, 21, and the number in C is 18. Now, if we think about adding all those together, when we add the 25, we've added on these 4 sections. When we add on the 21, we've added on these 4 sections. When we add 18, we've added on these 4 sections. So what we know that when we add on just the totals, we've counted certain sections more than once. So we need to account for that. So we need to be able to take away those sections. So what I'm going to do first of all is I'm going to take away the 9. That's going to take away one lot of that section of 9. I'm going to take away the 7, the number who said baseball and cricket, and that's just going to reduce that doubling up that we've done there. And I'm going to do the same for the 8 of the people between archery and cricket. So I'm going to take away a set of 8 people that have been counted too many times. So now what I can see is I've counted all of these regions once, which is great. So I've accounted for those to make sure that it's going to add up to 50. The problem that we've got is I have just deleted all the people in the intersection. So I need to make sure that I add that intersection, the number in A and B and C, back in to make sure that this is actually going to total 50. So if we think what we've done so far, I've got the number in A, the number in B, and the number in set C. I have subtracted the intersection of A and B, which is 9. I have subtracted the 7. That was the intersection between B and C. And then I've subtracted the 8, which is the intersection of A and C. But I've have to add in the intersection of all three because I have not included that when I've subtracted those other intersections. And this should give me the total of 50. And if we have a look, by adding that extra one back in, here the intersection, I have then been able to identify the union, the number in A or B or C. So if we do that, we can work out that we've got a total here of 40. 40 plus the number in the intersection has to equal 50. So the intersection of A and B and C is 10. So 10 people play all three as their favourite physical activity. So just as an edit to this question, it actually is 46 people were asked what their favourite physical activity was, and there was all 46 chose at least one of these activities. So just be aware in the previous part of the video, it had 50 written there, but it's actually using a calculation of a total of 46. So this is a really, really nice extension to that rule. So let's take a look at where we can use this idea of the either set in our use of permutations. So in our first example, we're going to have a look at essentially forming two sets and where these sets are mutually exclusive. Remember, we've talked about that they don't have anything in common, so there's no intersection or overlap between the different types of arrangements we can make. So how many different numbers greater than 400 can be formed from digits 3, 5, 6 and 8 if repetition of digits is not allowed? So what I'm going to do is consider the fact that we've got 4 digits, so we can do 3-digit numbers and 4-digit numbers. So I'm going to make them my two sets. So first of all, I'm going to consider my set A, my 3-digit numbers, which is completely separate to any 4-digit numbers. So I'm going to have no overlap in my permutations here. So for my 3-digit numbers, I've got 4 digits I can place. Let's take that back. Can't have 4 digits. My number's got to be greater than 400. So in my very first space, I can't use the digit 3. So in fact, I've only got 3 digits that I could possibly place here. My number can be 500s, the 600s or the 800s. Once I've placed a 5 or a 6 or an 8 here, I've then still got 3 digits that I can use because then I can include the digit 3. And then once one of those is used, I've got 2 different digits left. So I've got 3 times 3 times 2. I've got 18 arrangements. Now let's consider 4-digit numbers as my separate set here. Now, obviously being a 4-digit number, it's well above 400. So I've got 4 digits I can choose to put first. Once I use one of those, I've got 3 left and then 2 and 1. This will give me 4 factorial and 24. Now, if we actually listed out all these 3-digit and 4-digit numbers, we would have no common permutations here. No common arrangements, which means there's no intersection between these sets. They're mutually exclusive. So that means I can simply add these together. All of A and all of B will give me 42 different arrangements. Let's have a look at our second example where they're not mutually exclusive. So we're going to have to use our inclusion-exclusion rule. So we've got a security code of 3 digits is to be made from the set of digits 0 to 5 or from the set of digits 3, 4, 5, 6, 7, 8, 9. So how many possible codes are there if the numbers cannot be repeated? So straight away what we notice is we have an overlap of 3 digits. So when we make the code, they either have to come all from, we could call it set A, or they can come from set B. But what we notice here is we have a little bit of overlap. But let's consider each set separately. So our 3-digit code, we've got a choice of 6 digits and 5 and then 4. So 6 times 5 times 4 will give us 120. If we make a 3-digit code from set B, because we have 7 digits here, we've got a choice of 7 and then 6 and then 5. So we can use our multiplication principle to get 210. But what we have to remember in this situation is that we have some arrangements like the code 345, 354, 453, etc. that exist in both of these totals. So we actually have to take them out. So we want to find out how many are in set A and B. How many of those? Well, if we think about it, it's 3 numbers that are overlapping. So the different arrangements with those 3 numbers is going to be 3 factorial or 6, the 3 and the 4 and the 5 as digits. So using our rule of A or B, we could say the number in A and the number in B, take the overlap of arrangements that we don't want to add on twice. So we've got 120 plus 210, take those 6, that will leave us with 324. So in our third example is taking this idea of separating into 2 different sets and being careful whether there is any repetition of permutations or not. So sometimes in a situation we're forced to create that partition. How many 4-digit even numbers greater than 4,000 can be formed using the digits 0 to 8 inclusive, which means you can include 0 and you can include 8. So when I draw my rectangle and I think about where I can put my digits, I notice that in the very first box, to be greater than 4,000, I've got the choice of digits 4, 5, 6, 7, 8. And in the last box, to be even, the 0, 2, 4, 6 and 8. But as I've highlighted in blue, you can see there is a clash of the digits 4, 6 and 8. So what we really need to consider is if I put 4, 6 and 8 as my starting digit, then I won't be able to use one of those as my even number at the end. So I'm going to partition these sets so that they become mutually exclusive. I'm just going to consider starting with 5 or 7, and I'll be able to use all the even numbers in the end to consider, and then a different set where we talk about starting with the even numbers and then also ending in the leftover evens. So if we have a look at my set A, I'm going to create my box for my 4 digits. If I start with 5 or 7, I've got 2 numbers that I can consider to use here. And once I've used that digit, I've got 7 other digits that I can, let's take that back. First, then I have to consider my even digits. So I've got 5 even digits that I can put in this end box, 0, 2, 4, 6 or 8. So once I've used a 5 or 7 and then one of the even numbers, of those 9 original digits, I've only got 7 left to choose. So I can say 7 choices and then 6. So I could say 2 times 7 times 6 times 5, and that will give me 420. Or my other option is where if I want to start with 4, 6 or 8 being greater than 4,000 and any evens that are left over. So if I start with 4, 6 or 8, I've got 3 numbers to choose from. And once I place one of those even numbers, then of the 5 even numbers, I've only got 4 evens left to put as the end number. Once I've filled these 2 digits, of the 9 digits, again I've only got 7 digits left to choose from to arrange. So I've got 3 times 7 times 6 times 4, which gives me 504. So here I've got my set A or set B, and I don't have any overlap or in these different arrangements that I've calculated here. So I can add these together to get a total of 924 different arrangements because I've partitioned them so that they didn't have anything in common. In our final example, we're going to have a look at this inclusion-exclusion principle in full swing, if you like. So I've got a group of 6 boys and 6 girls to be arranged in a line for a photo. I want to know how many arrangements have a girl to the extreme left or a boy to the extreme right. Now, because we've got this idea of the or, the union, we have to consider the situations where the girl is on the extreme left and a boy is on the extreme right, or both. So it's taking us back to the idea of the Venn diagram. We could call set A having a girl to the left. We could call set B having a boy to the right. But there will be some permutations or arrangements where there's a girl on the extreme left and a boy on the extreme right. But what we want to do is find the or, the either of these things happening, which I've highlighted those 3 sections in blue. So what I'm going to do is consider the idea of our addition principle. So I'm going to call A the girl being to the extreme left. So if I represent this by a rectangle, I'd have a choice of 6 girls I could put to the extreme left. And once I place her, I can place the 11 leftover students in any sort of arrangement. Now, if I consider set B being the boy to the extreme right, I've got 6 boys I could place in that position. And then once I place a boy there, I've got 11 students to then arrange in 11 factorial ways. So now we need to consider the girls to the extreme left and a boy to the extreme right. So when arranging our 12 people, we'll have our 6 girls choices on the left and 6 boy choices on the right. And once a girl and a boy is placed, then we've got 10 other people to arrange in 10 factorial ways. So now when we're trying to consider finding the number of arrangements that have a girl to the extreme left or a boy to the extreme right, we're going to total up our numbers with girls to the extreme left, which was our 6 times 11 factorial. So that's taken care of that whole circle in our Venn diagram. And then we're going to add in boys to the right, which is the green section of our Venn diagram. And then we want to take away the intersection because we've included that twice. So we're going to take away that 6 times 10 factorial times 6. Because we're dealing with quite a few people that we're arranging, we end up with a very, very large number. And that is 348,364,800. So I like this question because it really brings together the idea of how we can use that inclusion-exclusion principle when we're dealing with permutations, and how we can also quite easily represent it on a Venn diagram. So now what I'd like you to do is have a go at the following 4 questions that you'll find on the next page. So pause the video, have a go at them all, and then come back and check your answers. And then we'll discuss these in our next lesson. Just 3 questions to check.